I'm going to go over some of the problems we had in chapter 4.1 through 4.4 on your homework. First problem we're going to cover is the function f of x equal x squared plus 4. X is greater than or equal to 0 is a one-to-one function. So if we look at f of x equal x squared, that's called a quadratic function, and its shape is called a parabola. So we've graphed plenty of these, and we know it's kind of that U shape. If I look at the entire parabola, it is not a one-to-one function, and so it doesn't have an inverse. But in the real world, we define domain and range. It's not an abstract concept, much like it is when we're just looking at functions f of x, g of x. So for example, an analyst models the relationship between a company's advertised spending, x in thousands of dollars, and its stock price, y in dollars, using the equation f of x equal negative 0.05 x squared plus 3x plus 40. Here the domain is 0 to 30,000 being that's your x. We're going to restrict the domain to non-negative values since spending can't be negative. We can't spend negative money. We're going to have an upper bound of 30 represent the maximum advertising budget for the maximum stock price. This model indicates that stock prices benefits from advertising up to a point before additional spending becomes counterproductive. So if I look at my graph on my domain, it's just a piece of that parabola from x being $0 to x being $30,000. So when x is $0, the stock price is going to be $40 if we don't spend anything on advertising. But if we spend $30,000 on advertising, the stock price is increased to $85. Now if we continue to look at that parabola after 30,000, it starts to decline. So that's why I restricted it to be increasing. So back to our function, our abstract function doesn't have any story. We just have f of x equal x squared plus 4, but they do make a note that x is greater than or equal to 0 and is 1-to-1. So that's half a parabola. It's on the positive side of the x-axis. The domain is given. X is greater than or equal to 0. And if we look at the graph, we can see that y is going to be greater than or equal to 4. So since this is 1-to-1, an inverse exists, so we can find that inverse. And these steps work no matter what the function is. If we want to find an inverse, we start out with replacing f of x with y. So we have y is x squared plus 4. The second thing we do is interchange our x and y. So y becomes x, and x becomes y. And then we solve for y. So I'm going to subtract 4 from both sides. Since I have a y squared, I want to solve for y, so I'm going to take the square root of both sides. But when we take the square root of both sides, we end up with this plus or minus. And we have to determine, well, is y going to be positive or is y going to be negative? Now, in some cases, y could be negative. Well, let's look what happens with our function. So we know the domain of the function, which is our x values, is 0 to infinity, and the domain of the function is the range of the inverse. So the range of the inverse is 0 to infinity, which means our y values are positive. And so then our inverse function is the positive square root of x minus 4. And if I graph that, I can see my function, x squared plus 4. I can see the inverse function. And I can see that they're a mirror image around the line y equal x. Now make sure you have a good xy axis system that actually models these. So I wouldn't want my x's to go to 50. Or I wouldn't want my y's to be too small. So you wouldn't be able to see the function. So my x's are going from 0 to, looks like 13. I probably should have made my y's go from 0 to 13 also, just to get a little better view of that. The next problem was composite functions. So I think you guys did a pretty good job of composing the functions, but then you had trouble with the domain and range. So I'm just going to do the first one, f composite g. When I compose functions, I'm taking one function and replacing it for my x and another function. So f composite g of x, wherever there's an x in my function g, I'm going to replace it with my x and f, I replace it with my g. And this thing is going without me. I can't go backwards for some reason when I'm recording. Alright, so when we solve this function, first of all, x can't be 3. We can see that here. But I have to take this entire denominator, and I have to say, well, that can't be 0. So my x plus 2 over x minus 3 plus 1, that can't be 0 because that's in the denominator of f composite g of x. And you can make the not equal symbol. I'm going to subtract 1 from both sides. And then I'm going to multiply both sides by x minus 3. And I'll move over a little bit here. And don't forget parentheses, because it's a negative all this. And so I have x plus 2 is equal to a negative x plus 3. On simple linear, we can solve this by adding x to both sides, so that gives me 2x. Subtracting 2 from both sides, so that gives me 1. Oh, and we want a not equal here. So I see x cannot be 1/2. So I put that's your vertical asymptote, x equal 1/2. But I also looked at evaluating this a composite function at 3, and you can see it gives me undefined. Another function, finding the inverse. This one's a little bit easier, but some people missed this one. Here we have a linear function, f of x equal 12x. So linear functions are going to be 1-to-1 as long as it's not a horizontal line. A horizontal line is not 1-to-1 for because every x goes to the same y. But a slanted line is going to be a 1-to-1 function always. So we want to find the inverse, and we go through those 3 steps. Also note that the domain and range of 12x is going to be negative infinity to infinity. So the inverse is going to be both domain and range, negative infinity to infinity. So step 1, I'm going to replace my f of x with a y. Step 2, I interchange x and y. And this again is simple linear, so that I'm going to divide both sides by 12, and there's my inverse. So the inverse of a linear function is going to be a linear function always. Again, unless it's a horizontal line. And we can plot these two functions in the line y equal x. I plotted a few ordered pairs so you can see the ordered pairs switch. 1, 12 becomes 12, 1. And negative 1, negative 12. On the flip side is negative 12, negative 1. And that's what an inverse does. Flips those ordered pairs. If I want to know if a function or a set of ordered pairs is 1-to-1, I look at all the x's first. If all the x's are different, it's a function. And then I look at all the y's. If all the y's are different, then it's a 1-to-1 function. So this function is 1-to-1. Another question was this graph. It was a parabola, and it was asking, is this determine if this function is 1-to-1? Well, if we have a graph, all we have to do is draw a horizontal line. And in this case, the horizontal line is touching twice. So that's telling me there's two y values, the same y values, for two different x values. So